In our last lecture, we discussed um, photoelectricity, and we concluded that by introducing stopping potential. So today we want to conclude our discussion, as we promised in our previous lecture in physics, that we're going to talk much about stopping potential. The question is, what is stopping potential? It's actually electrical work done, right, on a moving charge in our attempts to transfer the charge from one point to the other. So stopping potential is the work done against the charge when it is moved from one point to the other. All right. So um, we said last time that when a piece of metal is on the earth, seated inside a hole on the surface of the metal, all right, when the radiation of the sun is focused on this piece of metal, all right, this is metal, this electron can be ejected, all right, with maximum kinetic energy, all right. So for us to be able to bring it to a point, say point A, work has to be done against it to bring it to this point. So our definition will be the kinetic energy of the electron will be equal to the work done against the charge. All right. So the kinetic energy, which is half mv squared, this is velocity, is equal to the charge or electronic charge times the voltage times the voltage. All right. So this voltage can be referred to as the stopping potential. All right. So if we make it the subject, the stopping potential, therefore, is equal to mass of electron times the square of its maximum velocity divided by 2 times the electronic charge. So this is the formula for determination of stopping potential, in case you're asked to. So this is what we use to calculate the stopping potential of a charge, right? Then we know that, note that our E, which is the energy radiation, the radiation is equal to work function plus maximum kinetic energy. If we make kinetic energy subject, we have our kinetic energy maximum is equal to energy minus work function. Please, we are interested in this equation. I will call it equation 1. This equation is very interesting because it can help us by some other factors. It can help us to be able to determine the Planck's constant and some other physical quantities, especially when we make reference to the graph of the energy or potential difference against the frequency of radiation. And watch out, see how that goes. Don't go anywhere. So we come here. We want to analyze what the equation stands for. So we have the kinetic energy. Our K, kinetic energy, is equal to QV, right? From what we did there. And our energy of radiation is Planck's constant times frequency. So put all of these two, put in equation 1. In other words, we substitute these two things into the equation 1. So what we're going to have is our QV is equal to, we have HF minus W. If V is the subject, then we have H over Q times F, all right, minus W0. Okay, so this actually helps us, all right? If you analyze this equation very well, it looks like an equation of a linear graph. How does that work? So if you the general equation of linear graph is imported here. You're going to have m times x plus c. Okay, so this one is a dependent variable on the vertical axis. Then h over q, all right, stands for the slope of the graph. And then the frequency stands for x. Of course, oh, sorry, this is supposed to also be over q because we divided each of these terms. So this one now stands as the intercept. Now, with this analogy, all right, it becomes easier for us to note that this equation that we arrive at, this very equation, is actually a straight line. So just like we would plot y against x every other time, we can plot the PD, the varying PD, against frequency, all right, in this case. So if we try to do that, all right, this is not to scale. This is V axis, and then this V is in volts. And then we have this one as frequency, and it's expressed in hertz. All right, so if we plot, all right, if we plot the graph, this is what we will experience. Okay, assuming your points are scattered around the graph like this. This is what it will look like. And then here, this point where the graph line crosses the frequency axis shows to us that that's this one shows f0, and we told us from last lecture that our f0 is actually a threshold frequency. All right, so our f0 is equal to threshold, frequency. All right, and then from this graph, where the graph passes through y-axis, this graph is actually the intercept. This point is actually the intercept, and from the interpretation here, intercept stands as the intercept is with respect to the vertical axis. All right, so whatever we get from the intercept here can be equated to this. So this one is equal to our intercept, and intercept either C or I. Look at how so beautiful the analysis looks like. So the next thing we're going to do, we now say that we know that if we want to find the slope of a graph, this will be V1, this will be V2, your F1, and then this one is F2. So generally we define slope of a straight line graph as the change in the vertical divided by change in the horizontal, right? So in this case, what it means is that our V1, our V2 minus V1 is equal to F2 minus F1, all right? This value now is equal to H over Q, because what it means that this result is equal to this. And then we say that change in the PD over change in the frequency is equal to H over Q. So if you cross multiply, we say therefore the Planck's constant is equal to change in voltage, all right, over change in frequency times electronic charge. We'll be able to do that. So from this equation, all right, we are able to determine the Planck's constant, even the electronic charge, and so many other variables that you may be asked to find. You see how so applicable it is to practical aspect of physics. This is very interesting. You take your time to learn it. I hope you learn it.